So thank you for the introduction. So I'm very happy that we can finally discuss string field theory in person, and I would like to thank the organizers um, so, uh, for this conference that for this discussion can happen. I also take this opportunity to thank the organizers for the online conferences in the last few years, which were crucial for continuation of these activities. So, and I'm honored to be the first speaker of this conference, and I'm going to talk about correlation functions of quantum field theories using homotopy algebras based on this paper. And I also briefly mention the work in progress related to the application of this formula for the renormalization group flow. So can you hear me okay? I think it's a little bit louder. Okay. So let me go to the next. It doesn't change. In a few minutes. Okay. Oh, no, I think that's all right. Okay, so I let's start with the introduction. So in quantum field theories, like phi cube theory with this action, so it's difficult to find the pointer by myself. Okay, and so when we calculate on shell scattering amplitudes, we first calculate correlation functions and use the LSD reaction formula to get the scattering amplitude. Right? In string theory, we calculate correlation functions of the on-shell vertex operators integrated over the modular space. Right? In the case of open bosonic string and 4-point function, it is 4-point scattering, it is something like this. And we can use string field theory to reproduce this amplitude from an action like this. And this is the expression in the language of string field theory. So, but when we write action in terms of homotopy algebras, such as A-infinity algebras or L-infinity algebras, expressions in the previous slides can be written in a universal form. So on-shell scattering amplitude in perturbation theory are universal for both string field theory and also quantum field theories. So I'm going to explain later that the action can be expressed in terms of a linear operator with Q plus M. And then when action is written this way, the three level scattering amplitudes can be written some universal formula. And for loop amplitudes, we need a little bit one more ingredient in this denominator. I'm going to explain this. So as you know, so explicit calculation of loop amplitudes are in general difficult in string field theories, open and string field theory. So I wanted to get some insight from some exercise from the ordinary quantum field theories. So that's part of the motivation for this. So especially I myself didn't work on the loop level amplitudes in this homotopy algebra, using homotopy algebra. So I wanted to make sure that it works. And then, but then just one slide of digression. So as some of you might have heard from me a few years ago in Florence. So I wanted to provide a framework for proving the ADS-COT correspondence, and I wanted to construct a complete theory before taking the energy limit of the events. You may think that such a theory would be open-closed superstring field theory, but my claim is that it can be described by open superstring field theory with a source term for gauge invariant operators. If you wanted to know more about this, here is a written up for the talk I gave at the Florence. And then, so the long-standing problem of constructing action involving Raman sector has been overcome in superstring field theory. So I mentioned two papers. My paper with Hiroshi Kunitomo and Ashok Sen. So basically, there are two ways to take care of the kinetic term of the Ramon sector, and then there are very nice developments afterwards. So, given this motivation, I should say that I'm very serious about quantizing open superstring field theory. So this is the motivation for this work. But then today I'm going to talk about the correlation functions. So in addition to the scattering amplitude, uh, I, I I found that the correlation functions of scalar field theories can also be described in terms of homotopy algebras. And then I'm going to explain the explicit expression for correlation functions of scalar field theories using the quantum infinity algebras I presented in this paper. And at the end of the talk, I briefly mention its application to the renormalization group as well. So my slogan is something like this. So let's rewrite the textbook of quantum field theory, like textbook by Sredniki, and which I use for the quantum field theory course. So let's rewrite textbook in terms of homotopy algebras without using the canonical quantization or the path integral. So here is the plan of the talk. So I just finished the introduction. I'm going to explain the infinity algebra, then present the formula for correlation functions. I'm going to show you explicit calculations and show that the string addition equations are satisfied. Then here's the application to the renormalization group. Then I conclude the talk. So infinity algebras. So open bosonic string field theory is described in terms of string field, which is a state of the boundary conformal field theory. The Hilbert space, I denoted by H, can be decomposed based on the Gauss number, like this. And the classical action is written in terms of psi in the Gauss number 1 sector. Then consider an action of this form. Right? So this bracket is a BP inner product, and Vn is an n string product, and the G is the coupling constant, or string coupling constant. And this action of this form is invariant under the gauge transformation with the following gauge transformation, where lambda is a gauge parameter in the Gauss number 0 sector. Right? If the multi-string product Vn satisfy following relations, then the action in the previous page, this action is invariant up to some order, maybe up to it is just up to G cubed order. So then this relation can be extended to higher orders, and they are called infinity relations. So in this talk, I skip all the discussion of the cyclic properties. So you somehow didn't work. Okay, thank you. So where was I? Okay, so in open bosonic string field theory constructed by Witten, the V1, which is one string product describing a kinetic term, and V2 given by the BS operator and the star product. Then the infinity relations are satisfied without higher product because of these three relations. And the set of multi-string products in satisfy infinity relations for the open string and the L-infinity relations for the closed string can be constructed from appropriate decomposition of the modular space of Riemann subsets, as we learned from Barton Seeger long time ago. So these relations are complicated. But by the way, some of you might have heard the same thing many times, but this is the first talk, so I think it's good to explain that what the algebra. Okay. Especially some of you may know better than me. So let me describe infinity relations in a more compact and efficient way. Okay. So these relations are rather complicated. So let's try to simplify the description of infinity relations in 3 steps. So step 1, so we introduce degree, which is the opposite of Grassmann parity. So it is defined mode 2, but this is the Grassmann parity. So if it is Grassmann odd, it's degree even. It is Grassmann even, it's gonna be degree odd. Okay. Then I gonna adjust uh, and introduce a kind of simplistic form from a VPGNA product. And I gonna denote M1, M2, M3 for the um, multi-string product in terms of graded with respect to degree. Okay? Then infinity relations written like this. So Grassmann parities of Vn are not uniform, but in terms of Mn, they are all degree odd. So that's is useful. The step 2 is that I'm going to introduce tensor product of a Hilbert space or vector space H. We denote the tensor product and copies of H by this symbol. And then for n string product, Cn, we define corresponding operator Cn, which maps H to the n into H by this. So this seems rather trivial, and then you may not find why this is useful, but I'm gonna explain using the example. So okay, so also I also introduce a zero string space denoted by h to the zero. So this may not be familiar, so let me explain a little bit more. So it is a one-dimensional vector space given by multiplying a single vector basis, which I denoted by 1 in this font by complex numbers. So this vector 1 satisfies this relation in the tensor algebra. So then using this tensor product, so this is one of the infinity relation. So then we can, for example, you can use, I don't even see the mic. Okay, let's see. Okay, so this term can be written this way. So now this is an M1 acting operator over H2. So this is a map from H to H, H squared to H, right? Okay. Then so maybe this term can be written this. I think this one. So this term can be written this way if I denote the identity map from H to H by 1. So there are many ones that I use this identity map from this font following that, I think. Okay, so then this can be written this way, and also maybe this term, right? So this term can also be written this way. But then when M1 acts on A2, M1 passes by A1, and so that cancel this sign. Then on the right hand side, there is no sign. So yeah. So actually, this simplifies a lot. Okay, so then this relation can be written this way. There are no signs, and also you can. So this holds for any A1 cross A2. So I can drop A1 cross A2. So that's why we can simplify the integration. This. Then the step 3 is the introduction of the co-derivations. So it is convenient to consider the linear operators acting on the vector space TH, which is some of these vector spaces. So we denote the projection operator onto H to the n by pi n. Then for a map Cn, which from H to the n to the H, we define an associated operator boldface Cn acting on this space Th as follows. So if n is less than the m, it's vanishes. Therefore, the action of the H to the n is the same as the normal Cn. And for the action of the sector h to the n plus 1 is given by this. And for the h to the n plus 2 given by this. So I think you understand the rule from this example. Then operator acting on this space th of this form is called a co-derivation. Then we define the board face m, which is the sum of the co-derivation m1 plus m2 and m3. Then co-derivation mn associated with, by the way, this board face mn is associated with the n string operator mn. Then the infinity relation can be compactly expressed in terms of m just square is 0. So this is very simplified. The information on the action can be encoded in this degree of co-derivation, which is square to 0. Conversely, we can construct a gauge invariant action from a degree of co-derivation, which is square to 0. So this is the very useful description of the infinity algebra. So then let's consider the projection onto subspace of H. So in this case, the homotopy algebra is a very powerful, and it turned out to be a very useful tool. And there are several projections we can consider. For example, projection onto the on-shear states. So that is relevant for the on-shear scattering amplitudes. And I think this was originally discussed by Kajiura. And also projection onto the physical sector. So it is useful in considering the mapping between the covariant light string field theories, discussed extensively by Ted and Hiroaki Matsunaga. I think I'm going to hear more about this in this afternoon by Ted. And also, we can consider the projection onto the masses sector, which is relevant for the low energy effective action. So Ashok Sen was discussing this effective theory, and also the Harold, Carlo, Martin, and Jakub, and I also my group is students discuss this kind of thing. So there are several motivations, several directions, but then the tool we can we can have a universal tool for this description. So for this purpose, we decompose m by q plus m. So capital M is decomposed to q plus lowercase m, where q describes the free theory and m is co-interaction. Then we consider projection, which commute with q. Then, so I denote the projection operator by p, which scale to, as this is the definition of the projection, and which commute with a BS. It's not it doesn't necessarily a BS operator. It's an operator described in the kinetic term. Then we can promote the p to the board face p, which is the operator on th this way. And then the these relation can be promoted to the relation for the board force operator p and board force operator q. So I think I cannot turn on page. Oh, this time I can do it. Okay, sorry. Then one more ingredient is the propagator. So in the context of projection onto the masses sector, the propagator, which I denote by h, for the massive field is given by this. Then in general, we consider h satisfying the following relation. So for then given the projection, we consider h satisfying this relation. Okay. Then we promote h to the board face h acting on th in this way. So this may look similar to the co-derivation, but if you notice that we have p to the left of h, to the right of h, and the identity operator to the left of h. So this is a key to satisfy these relations. So again, these relations are promoted to the relation for the board face operators q, p, h, and 1 like this. Okay. Again, there's another the identity operator, which is identity operator on TH. So this might be different from the notation by Ted. I prefer this. Uh, So okay, so then here is the important point. So the um, so the theory after the projection inherits the infinity relation from the theory before the projection. So if we have a projection, the operator which I was also, if we have a theory uh, has an infinity structure described by Q plus M, then theory projected by the theory after the projection, the infinity it also has an infinity structure and described by this operator. So this is very universal, and then the derivation of this infinity structure from this is known as a homological perturbation lemma. So this is the universal formula. So now I wanted to move on to the formula for the correlation function. So let's consider phi cubed theory in D dimension, and then to describe the action in terms of infinite algebra, we introduce two copies of the vector space of a function of x. I denote them by h1 and h2. So this is roughly following the Gauss number convention of open string. So h1 and h2, and then h is just sigma h1 plus h2. Then we define omega q and v2 like this form. So so the infinity structure of the classical action is described by this time. So V2 describes the cubic term, and then so this is the infinity structure described by Q, just Q plus V2. But actually, the infinity relation, a trivia is satisfied for this theory with that, because this theory doesn't have any gauge symmetry. So I only wrote the non-vanishing action of the operator. So for example, when B and okay, Q acts on the element of H2, it vanishes. So Q squared is zero in it's rather trivially. Also, and B2, when B2 of something, phi 1 plus phi 2, but if one of them is in the H2, it vanishes. So if you try to act operator twice, then the second action of the operator always vanishes. So in that way, all the infinite relations are trivially satisfied. Sure. Yeah. Uh, mhm, mhm. Yeah, but then we are talking about the theory without gauge invariance. Uh-huh. Yeah. Okay. But I'm at the moment I'm talking about the action. Q is describing the action. Mhm. I'm not talking about the solution to the action. Uh-huh. So am I supposed to repeat the action question? So, oh, that might be difficult than answering the question, right? But yeah, so yeah, um, new, uh-huh. Is it better? I Is it okay? I don't even. I can't. Okay. Mm-hmm. Yeah. So I got a question about the. It's difficult. Maybe you can discuss. later after. But then, so there are. I'm just at the moment. I'm just talking about um, uh, the Q describe the kinetic term, right? And then anyway, it is rather okay. It's square to zero uh, because action of Q on any element of H2 is zero, right? So, and uh, action of Q on H1, element of H1 can be non-vanishing, but then second action of Q is zero by definition. So it is rather trivial. So there's no point of writing pi cubed theory in terms of so maybe there are some. Okay, do you have? So maybe you can have a mic because I wanted to.
Yeah, we have a lot of time, so we can take a couple of questions.
Okay. Yeah, no, I was just wondering whether, since in this trivial example, this B2 is clearly commutative and symmetric, you can also reformulate everything in L infinity language
Yeah,
instead
yeah,
of
yeah.
A
We can
infinity.
also write describe this by infinity algebra as well. But just I don't know, my motivation is to quantize open string history. That's why I use infinity algebra. So almost everything can be translated into the language L infinity, I think. Thank you for the comment. Then let's see. Where so okay. Then when we consider on-shell scattering amplitudes, the description of action itself in terms of homotopy algebra seems rather trivial, and there are no useful things for the theory without gauge invariance. But then when we consider on-shell scattering amplitude, we use projection, onto the on-shell states. Then, okay, so in this case, h on this phi x is given by this Feynman propagator. Then, then we can use the universal formula I just mentioned, right? In the case of the projection onto the on-shell states, so if you, okay, I think. So this is a universal formula. But for the projection on the on-shell scattering amplitude, so this term vanishes. So we have maybe I got too far. So so this the on-shell scattering amplitude can be described by this operator, right? Can be calculated by this. Then we want to discuss the quantum theory. So that's our main point in this discussion. So we need to include, so first of all, we need to include the counter terms. So technically, I denote the counter term is in this part, Q plus M. Right? So M, not only B2, classical cubic interaction, but also M includes the information on the counter term. Okay. Then on-shell scattering amplitudes, including loop diagrams, can be calculated from this formula. So compared to the doesn't work. So compared to this expression, so I replaced B2 by M, but in addition, this is an important ingredient that reproduce the loop diagrams. So I'm going to explain the action of U in the following way. So this operator U consists of maps from H to the N to the H to the N plus 2. So when we use the okay, so the vector space H is given by H1 plus H2. This operator U incorporates a pair of spaces vectors on H1 and H2. So this may be a little bit okay. So when we denote the basis vector of H1 by E to E with the upper index alpha, and where alpha is the level of the basis vectors. And for H2, we denote the basis vector by E sub alpha. Then repeated indices are implicit sum over as usual. Then, for example, in the concrete examples, I use e to the minus IPX and e to the IPX for the basis. Then summation over the alpha is denoted by the integral. Then action of u on the h to the 0 sector is just given by this. The u on the action of u on h is given by. So you can just incorporate e alpha, e upper alpha, and e lower alpha in all possible ways, just taking into account the degrees. So this is the action of u. Then infinity. Okay. So I will not write explicit formulas, but infinity algebras are extended to quantum infinity algebras in the quantum theory. But again, the quantum infinity algebra, also quantum infinity relations are again trivially satisfied for this theory without gauge symmetries. Pretty much the same reason for the classical theme. Then, okay, so if we recall that the projection onto the massive sector corresponds to the integrating out massive field, so carrying out the path integral completely should correspond to the projection to nothing, right? P is equal to 0. Then associated operator P on TH correspond to the projection on the sector H to 0. So if you so this, okay. So if P is 0, so this or the term vanishes, so that this is only non-vanishing. Okay. So you may think that this projection will produce a rather trivial theory, and I think it is the case for the classical theory. But it can be non-trivial for the quantum case, and in fact, it is exactly what we do when we calculate correlation function. So then, I think it's certainly better to use. We can use the Euclidean or Minkowski case that I'm gonna explain in, more explicitly in the Euclidean case. So consider the scalar field theories in Euclidean space. Then okay, so then we define. Okay, so in the case of Minkowski case, so this is the important part of the important part. And in this, I think this is the correct the convention for the Euclidean case. And then I denote this important piece by F. Then, and so when, okay, so then this can be written as PMFP, right? So while PMFP vanishes, but this F itself is non-vanishing. So if we consider the projection to nothing, to 0, then this operator, the whole operator vanishes, but the F itself is non-vanishing, and then this operator is actually plays an important role, the central role in reproducing the Feynman diagrams. So my claim is that the information on correlation functions is encoded by this F. Actually, it's action of F on the sector H to the 0, associated with the projection P equals 0. So more explicitly, this is the formula for the correlation functions. So correlation functions are given by the pi n f1 with this the omega n, which is just a product of omega. So this formula may look complicated, but basically it said that the information is the correlation function is given by pi n f1, and its endpoint function is simply replace x with xi in the ith sector of Hn. So I'm gonna explain this replacement rule in the next slide. So suppose for example, if you wanted to consider the 3-point functions, right? So then we use pi 3 f1. Okay? Then suppose it is given by this, by this. Then this formula may complicate it, but the upshot is that the 3-point function is simply given by this by replacing this x by x1, this x by x2, and x by x3, and then no tensor product symbol. So essentially, if we calculate this guy, then we got the correlation function. So the question was how.
Yeah, so I was just asking how. Yes, thanks.
So
Just to see how this thing was.
Okay, so omega n is just a product omega, and please.
I'm sorry, I didn't follow how this correlation function follows from setting p equals 0.
Uh-huh.
Where's the p equals 0 coming
P equals
in?
0. Okay, so so maybe you will see in like explicit example. So that's I gonna. So basically, when we calculate correlation functions, we do the path integral completely, right? So that's my logic. So I think if you compare the situation for the projection to the massless sector, which may be, I think.
Well, when you set p equals 0, I don't see how the dependence on x comes about. Or I don't know. It just looks a little weird. I just didn't follow this.
So in the classical case, we get nothing. But then in the quantum case, we have an operator u, which creates a states from nothing, right?
Right, but there are classical correlation functions, right?
It's quantum correlation function. That's my claim.
So it gets only the quantum correlation functions, or they like connected correlation functions, or what?
For example,
maybe this will be
it's
clearer.
really the so I literally say that this is a quantum correlation function.
Okay.
So when
so
we
the graphs which contribute are only the connected graphs, is that the?
So that's I'm gonna show you explicitly. So it's also contains a disconnected diagram as well, actually.
Okay.
Yeah.
Okay, thanks.
So that's good. Actually, this is a good part to convince Ted for my formula, right? So I'm gonna show you explicit calculations. So let's first consider the free theory, right? So in the case of free theory, so I don't have the operator m, and sorry. So f1 is just given by this, right? Then let's the action of h on phi is given by. So this is the definition of h for the Euclidean case, right? Then 2-point function can be calculated by pi to f1. Let's calculate this. Okay. Then if we expand this 1 over 1 minus hu, the only hu1 contributes for this projection, the sector from pi 0 to pi 1, sorry, pi 2. Okay. Then this guy can be non-vanishing, and actually this is just an, so u1 is e alpha times e alpha, and then h acts on only on this pair. So this is the, so I will skip the so if you have more questions, I can explain more in detail, but this is the upshot of the calculation, right? Then using the explicit basis, I chose, so I got dependence on x as this. Then we use the replacement rule. So I replace this x by x1 and this x by x2. Then we get the 2-point functions. Right. Is this answering part of your question? You say this is classical. Yeah, I would say this is tree-level diagram. So the Ted thinks this is weird because this is the class. So he's is a classical 2-point function. But by that I mean this is a tree-level diagram, right? Yeah. It is a free propagate. Yeah. So do I have a? I gotta so I didn't have a three-level diagram. So at later I gonna reproduce this one loop 2-point function, but then so this was the three-level. I thought I have anyway. But then if you put the h bar, this is this contains the factor of h bar, right? So in that sense, this is even this is the classical correlation function. It is quantum. This is a quantum. So,
Okay, I think I'm still confused about this p equals 0. So maybe you can. I missed something. Maybe you could go back and show me what your formula, your proposed formula for the correlation functions is.
Somehow this is very. Sometimes it's slow.
So your correlation functions.
Yeah, this is
your proposed formula.
Yeah. But if depends
so
on
what I don't understand is how that formula corresponds to setting p equals 0 in the homotopy transfer formula. Looks like you're just doing something different.
Okay, so f depends on the choice of h. H depends on the choice of p. My h is the h corresponding to p equals 0. That's my.
But then when you write this formula for the correlation functions, it's not somehow the homotopy transfer formula with p equals 0, which I guess does that even make sense, or would that be just trivial? Okay, so so when you're talking about p equals 0, you're just saying that you ignore the propagator term.
I'd rather reproduce the propagator term, right?
Yes.
So maybe.
Right.
So it's a homotopy transfer to almost nothing, right? So the solution to the classical Euclidean scalar field theory is just x equals phi x is equal to 0. So this is the projection to this vector.
Okay. Right?
And then H homotopy. What is there? H has a very nice name, right? So it's a homotopy retroact or something, right? Yeah. So if you consider the projection to the vector with phi x equals 0, then H should be given by this. That's my claim.
Okay.
So actually, to be honest, in the case of a projection of the on-shell states, is rather subtle. So formally, it may take the same. So we use operationally we can use the Feynman propagators, but I'm not 100% comfortable with that in the case. But then in the case of correlation functions, I'm actually more happier because this is just a projection to the p equals 0, and H will be given by this.
Okay.
should be given value.
Okay.
So this is actually a very important point. Yeah, this is rather subtle, but this is the main point of my discussion. So I'm happy to have more.
Okay, but now, okay, but H is not 0, right? Here,
H is not 0. Yeah.
but P is 0.
Okay, so
Now I'm just confused again. Now I am again not
okay.
following where
So
P
H
equals 0.
satisfy. Okay, so now you can just P to be 0, right? So QH plus HQ is identity.
Uh-huh.
H, this is trivially satisfied. This is
Uh-huh.
trivially satisfied. And H squared also 0. So that's so.
So if P is equal 0, it looks like then P has no cohomology.
So usually, so you consider that the cohomology is preserved, but then I'm not talking about that in that context. Yeah. So even for the projection to the massless sector, so we my understanding that we are interested in the sector, that we are interested in the theory without discussing the massive, the scattering massive state. We're just interested in the massive sector. I think it is the same thing. So
yeah, but I think the non-trivial question is whether you can find an H that satisfies this thing, because it looks like you are completely inverting Q even on the mass shell if you're doing this.
Functions you're avoiding the poles and the
no. That's why I'm talking about the Euclidean theory. In the Euclidean theory, there are no subtlety.
Okay.
Right?
Oh, I see. Okay. So
this is
so when in the homotopy transfer, when you set P equals to 0, then a lot of those terms that come from H acting on tensor products of states, a lot of those terms drop out. Is that important?
Sorry, I'm not sure if I understand.
So when H acts on a tensor products of states, it involves P, right?
You're talking about board face H?
Yes.
Okay.
So a lot of those terms will cancel. Just the one with a lot of those terms will drop out.
Yeah. So that's simplify the calculation. Let's see. So where is the board face H? Board face H? I cannot find it. Should be. I think this one, right? Yeah, that's right. So when P equals 0, this is gone. So actually, it's just only this term survives. And for H phi 3, this is gone. This only appears. So that simplifies. And actually, this is the source of the Wick theorem. Yeah, Wick theorem.
Okay.
Yeah. Is that answering your question? So,
I guess so.
Yeah, I didn't explain the
I'm
detail.
still not sure I see where P
So,
equals
for example,
0, what role that is playing in what you're saying, but
yeah, P equals 0 was
maybe it's we can discuss it later. I don't know if it's important or
yeah. Anyway, so okay.
Okay. So P equals 0 means heuristically that you are integrate out everything.
Everything, yeah.
Including the massless sector. And since you are Euclidean, you can do this thing.
Yes. In the case of Minkowski's case, there are some subtleties.
Because so the cohomology somehow is not seen in this Euclidean sector.
But that's the issue of definition of a quantum theory in the Minkowski case. So we assume, so we choose it's a definition of the choice of the vacuum in the quantum theory, right? So we usually consider the definition of the path integral, that the vacuum is unique. So in that case, we can consider the Minkowski space. And then technically, H is given by Feynman propagator. So that's the same, when you define the quantum theory so that requires some treatment for the definition of boundary behavior of the path integral, then we know that the upshot is the Feynman propagator just takes care of the contour theory with the choice of the unique pattern. Right? But anyway, so that's why I first wanted to convince myself and convince you in the case of Euclidean theory. In the case, much less subtlety. Right?
May I ask a point?
Please.
I haven't understood the role of a U operator. I have a completely miss. While the other terms are clear, what you are constructed diagrammatically, what is clear, but the U is, I haven't understood what it is doing the U, especially because in the formula you have presented, there is an H bar in front of you, and from what you said, it seems that it is connected to counter terms. Okay. But then you introduced the U in the free theory, where there are no counter terms. So I am completely missing about the role of the U, because it is going for H time n to H n plus 2. So I am not understanding what it is doing diagrammatically.
Yeah. So diagrammatically,
can you write on the blackboard? So
yeah.
Instead of going from, you have a nice blackboard, you could write whiteboard, okay.
But basically, okay, so you create, so let me try to use, this is whiteboard. So you create this piece of the Feynman diagram. That's why I denoted by you, right? So from nothing, so for example, M3 maps to H to the H cross H cross H to H, right? This is, okay, H3 to H. And then you, for example, creates, this is H to H cross 3, right? By adding pair of states, E alpha and E sub alpha, in addition to the phi. In the case of free theory, we still have this term, but we don't have this term. Yeah. So you can, okay. So even for the free theory, okay. So in the case of free theory, we don't have this term. This describes the interaction of the terms, everything. But this is present any theory in the contour case because you see H bar, right? In the free theory, we still have we need this term, right? So that, and then in the Euclidean case, I in the Euclidean case I dropped H bar because it can be described for in the statistical mechanics. You can use beta instead of H bar. So I set it as 1. But anyway, so this should be presented for the classical contour theory, free theory, and then I'm about to reproduce Wick's theorem. Okay, so I just explained how we get 2-point function propagator for the free theory. Then in the case of 4-point function, the free theory, I expand this, and then only this term contributes. Then, there are two actions of that U. So as you see, we now have a 2U, right? From 0, so you have something. So two pair of E alpha, and E beta, right? And we have two two H's, like, and it is, as Ted asked me before. So action of H is rather simple. So anyway, so this is, and also this reflects the choice of the P equals 0. Right? In the case of P equals 0, H basically appears only in to the rightmost place. So we get 3 terms. Then replace E alpha by this one into the IPX, and then use the same replacement rule. But basically, for example, one of the maybe first term is given by this. Then replace this one, x1, x2, x3, and x4. Then you get this formula. This is just a product of two propagators. And then there are three terms that consist of the evaluation of the 4-point functions in terms of Excel. Right? So this is the how we reproduce the correlation function of free theory. I hope up to this point, some of your confusion has been clarified. But I don't. It's already 1 hour, but I think we had a nice discussion, so maybe I can continue, right? Then actually, I almost tried to delete all the details, but then just in case I presented the formula. So we can reproduce the correlation function of the interacting case as well. So I chose 5 cube theory. Then also we need to include the counter terms. And so you should remember that M contains the classical cubic vertex and also counter terms. Then this is some details of expansion I cannot skip. I also skip this. Sorry. Then, for example, if we want to calculate 1-point function, we need to calculate pi1, f1, right? Then the upshot is that we got this formula. So this represents tadpole diagram, contribution from tadpole diagram, and also we have a contribution from the counter term. So and also it is important point is that the correct symmetry factor is reproduced automatically. Right? So this one here. And then usually we choose the counter term to cancel this 1-point tadpole order by order. But I just wanted to leave it finite to keep track of the appearance of one of the tadpoles. But anyway, so 1-point function is reproduced. And also, and in the process of calculation, so this particular combination appeared, which can be interpreted as the operator describing the 1PI effective action. So in terms of 1PI effective actions, we can reproduce 1-point function this way. Then in the case of 2-point functions, after skipping all the details, here is some result. It is described by the this guy, the linear term at 1 loop in the PF direction. Also, after the calculation, a new ingredient is this one, gamma 1 loop, which is given by this. So this is the action of the 1P and the term in the term. So I think I should theta to G. So this describes this kind of thing, right? So, and the 2-point function they are also reproduced, and also this also contains disconnected piece as well. The connected piece, and there's a 3-level one loop term, which is a connected part, and also a disconnected part. Disconnected part is just a product of the 2 particles, and the connected part has 2 terms, this one and this one. So I just wanted to convince you and myself that all the results in the textbook are reproduced, including all the factors, all the signs, everything. So that's I wanted to make sure, and I think I can do. And then, but we can actually prove that the correlation functions are reproduced at least in the perturbation theory by showing that my formula satisfies the Schrödinger-Dyson equation. So it is actually very simple. It's just follows from the structures of F. F is the inverse of this operator. So that means that this operator F times this one is the identity operator, and the identity operator is non-vanishing only for the action of the h to the 0, right? So this implies this equation. So this is the expression of the Schrödinger-Dyson equation in the homotopy algebra language. So again, I'm gonna skip the detail, but so this is this is translated to the endpoint function, n plus 1 point function, and this contains some interaction terms, and this contains u. So we have a pair of states in addition to the phi x1 to the phi xn. Then we use the this operator to replace these terms in terms of this variation. Then you get the familiar form of the Schrödinger-Dyson equation. So this is general proof that the correlation function. So my formula reproduces the correlation so satisfies the Schrödinger-Dyson equation, which is the equation of motion for the correlation function. Then let me try to discuss the application to the renormalization group. So actually, construction of board face H from H is not unique. So once we choose P equals 0 and then choose P to the this one, then in addition to the so let's consider the projection. In addition to the projection to nothing, I also introduced the projection to the mode below the energy scale lambda. Okay, then we then I gotta consider H as sum of 2 terms, H plus HL, where H is for the high energy modes, and this is the propagator for the high energy mode. So this is the projection to the energy scale up to P up to lambda, right? So this may be this is a projection to that sector, and this is the propagator for the low energy mode. So then we can write FP this way. So this may look complicated, but it's very simple. So let's see, I can use. So, or do I have an eraser for this whiteboard? Or I may use this paper. Yeah, I can use paper. So I think it's 1 plus A plus B inverse. So I think think this is 2. So this is 1, 2. So this is simple calculation for the matrices, two matrices A and B. Right? So in my case, my choice of H. Actually, by the way, this H satisfies the same algebraic relation as the previous choice of H. But this is given by HH plus HL. Then also these guys, HM and HM. So this piece are sum of the two terms, right? So it takes home basically 1 plus A plus B inverse, right? Then we factorize this 1 plus A plus B this way. And so it is the inverse of the two factors. So this gives you. So this is the formula I wrote. So I think this is correspond to 1 plus A inverse. And 1 plus A inverse also appears here. And this is P, right? So this is just a simple algebra, and this is the calculation in the simple linear algebra. But the point is that this is a little bit non-trivial, but you can, this expression can be written this way, where we can place the projection to p lambda here. So in other words, 1 minus p lambda, if you insert 1 minus p lambda here, it vanishes. Okay? That means that this guy, this contains all the information on the correlation function, can be written as a product of two terms, where this contains the path integral over the high energy mode only. And this guy is correspond to the path integral over the low energy mode, where this m lambda is given by this, basically this plus m. So this can be understood as a Wilsonian effective action at energy scale lambda. So the correlation function can be written by the two factors. So this is corresponds to the passing there over the high energy mode and the low energy modes. But in the case of low energy modes, you need to use the interaction at the energy scale lambda. Also, you can consider a sequence of projection, right? Sequence of projections. Then we can write the expression this way. So we have a several energy scale, right? Then the for example, if you calculate, expand this expression and then reproduce part of the Feynman diagrams, it's gonna, for example, take this form. So this piece, this region is for the M1, and we use, for example, the coupling constant in this energy scale. But this is a middle energy scale described by M2, and it may have this describes the Wilsonian interaction. So this may have a 4-point function or 3-point function with either different value for this energy scale. And so also HU can be decomposed depending on the energy. So there are some operator U creates the mode in this energy scale. So for this is a U for the low energy scale. So I think this is very nice. So the 3-point function can be written as a passing. This region is a passing there for the high energy scale. This is for the energy scale. And this is the low energy scale. So and then the good things about this kind of relation is that, so first of all, this I think this is a nice way of describing the renormalization group using the homotopy algebra, or in the language homotopy algebra. So I hope this is a very nice application. Furthermore, and when for example, I proved that the Schwinger-Dyson equation, that they are defined only in perturbation theory, so I don't expect to be convergent. But then if we use H or more this kind of thing, and then we also decompose energy scale and more in the narrow range, then this the correlation function written in terms of this H can be defined, can be convergent. So this kind of choice of H may lead to the non-perturbative expression for the correlation function, which I hope to explore more. So this is the end of the talk, and let me conclude. So the main result is that I propose a formula for the correlation function, endpoint function, in terms of pi n f1. Okay. Then, so I express the correlation functions in terms of and quantum effect algebra in perturbation setting. Then I prove that this expression satisfies the Schwinger-Dyson equation. It is just a simple consequence of this structure. So since the description in terms of homotopy algebra or the formalism tend to be elusive and formal, I think. So that's why I wanted to make sure that every concrete in details can be reproduced. So I hope I presented completely example of 5-cube theory. And also, validation at one loop can be reproduced correctly. So I think this demonstration let us convince ourselves that any calculation of this kind in the path integral or the operator formalism can be carried out in terms of in the language of quantum NFT algebra as well. So we can rewrite Fixed-book in terms of quantum NFT algebra, right? So but then I said that the formulas are universal, but it's almost universal because in my calculation, I assume that the vector space H consists only of two sectors, H1 and H2. This secretly simplifies a lot. So I need to extend, first of all, to include the gauge theory like Yamel, but then furthermore, we want to extend it to the certain field theory where all the goal sectors are present. So that should be important. But then, okay, that I have to say. Also, I said that I'm serious about quantizing open supersymmetry field theory, right? In the quantum theory, we need to pass integral over the Raman sector, which should be technically very challenging. So that's why I wanted to extend the formula for the quantum field theory to include fermions, Dirac fermions, which is now work in progress with a student of mine, Keisuke Konosu, who is in the online audience. So I think this is also important. But then my ultimate goal is to provide a framework to prove the ADS-CP correspondence using open supersymmetry theory with those terms for the gauge invariant operators. So this quantum treatment of open supersymmetry theory must be, so we need to really analyze. So for this to happen, we really need to analyze open string sector quantum mechanically. So quantum treatment should be important. So I hope this quantum NFT algebra will provide very powerful tools for this in the past. Thank you very much.
Are there any questions? Okay, I will do Ivo first because he's closer.
So thank you very much. It's very interesting. My question was about this object U, which you introduced. Do you think of it as an element of the algebra, or is more something that enters in your formula to compute correlation functions?
It is in, first of all, this is dual to the BV Laplacian, right?
Mhm.
So it is extremely important ingredient in the quantum theory.
Mhm.
Is answer the question?
Yeah, almost. I mean, but you don't say you wouldn't postulate any particular commutation. You know, yeah, in the A infinity algebra, which you showed at the beginning, you had all these commutators defining the infinity algebra. You wouldn't include the U in this.
Yeah, that's
in
right.
this-
Yeah. So in the quantum infinity algebra, it's gonna be not m squared to 0, but m plus u squared to 0.
Oh, you
I
put
think,
like
yeah.
this. So then, sorry if I may have one more, because it seems to me the way the U acts, it automatically symmetrizes because you know the two outputs.
Yeah.
So doesn't it automatically take you from A infinity to actually L infinity because you always symmetrize the outputs? You know what I mean?
So it's a very nice point. That's I'm also I honestly I don't understand. I don't
Okay.
understand.
Mhm.
But somehow my formula proves the string-Gaussian equation, which is symmetrized, right?
Mhm.
So it seems that so my conjecture is that there are some cyclic property in the pi n f pi m
Mhm.
where it's you know input is only cyclically symmetrized,
Mhm.
but the output is somehow completely symmetrized.
Okay.
That's very. I think we should be able to prove that. I don't have any good explanation.
All right.
That's very important point.
Thank you.
very much.
Hello. Is it does it work? So first of all, thank you very much for nice talk. I also like strong homotopy algebras. And so my question is related to, say, BV formalism, relation between BV formalism and what you're doing. Because, say, at the BV level, which is not, by the way, reviewed in the book that you want to write, you have a L infinity algebra, and the same way, computing quantum effective action can be thought as sort of minimal model theorem and so on. But then the main advantage is that you can treat gauge theories and so on and so forth. But okay, eventually the problem is to actually compute the integral or even get the integrand, say, through double copy or positive Grassmannian. So, but at the final point, you have to compute the integral to get the amplitude. And then I think
So
combinatorics.
which integral are you talking about?
Well, the loop integral. I mean, if you want to get amplitude, the actual work is not the combinatorics of all of that, but to compute the integrand. And so my question, so what is the crucial advantage of your approach based on A-infinity algebras as compared to, say, BV formalism, which is based on L-infinity?
I'm not sure if there is any. I think it's basically dual. So I don't know if there are clear advantage. But infinity algebra has been very so. But I think this formula I like this formula very much. It's very simple, right? Like yeah, this is very simple. And the BV in the description, the BV can be complicated. Yeah, and more algebraic, I think. And also tensor. So I think maybe one advantage is that the underlying. So I didn't explain anything about this, but then and there are tensor algebra acting on this pH. Basically, this is the main arena for everything. Then we have a simple associative algebra of tensor, the tensoring the thing. So that is very simple and it is powerful. And in the case of, it is also counterdetermined in the BV, but I think I feel this is technically, at least technically, useful. I'm sorry, it's not a very fundamental answer.
But can you extend your formalism to treat gauge theories?
I guess that should be fine. Yeah. So that in the case of I only so that is related to my last comment. So I just started by phi-cube theory, where the only difference is that the definition of the choice of the H Hilbert space. So H is so in the case of scalar field series or any series without gauge invariance, I only have we need two sectors. So in the B language, it's the field and anti-field. Okay? In the case of simple gauge theory like Mills, we need four sectors: H0, H1, H2, H3. And two of them are fields and describing the sectors. To describe the Mills in the quantum master action, so you need two sectors, right? Then there are two anti-fields. So there we need four sectors. In the case of string field theory, so we need infinite many sectors, right? Because, right? So it's the fields, anti-fields. These are all fields and these are all anti-fields. So the gauge symmetry of the string field theory is very complicated and irreducible. So we have a ghost for ghost and ghost for ghost and ghost for ghost for ghost and ghost for ghost for ghost, and they keep going. So that is complicated. But my hope, actually, my message is that so where is my beautiful formula? Where is my beautiful formula? Okay, this may be true, right? So okay, so when this is just a choice of different vector space. Yeah. The relation of action and then physical quantities can be universal. So that is that's why I'm doing this exercise for scalar field series to get good insight into the even for the calculation in the string field series.
Okay, thank you.
Okay, I have one questions again to this issue where we are projected to zero to see the correlation functions. If you would do that for a more general gauge theory, say like Yang-Mills theory or anything, would you also project to zero or on the cohomology of the kinetic operator? Or
so my claim is that when you calculate correlation functions of gauge theory, we should project the p equals 0. So that's for everything, for every theory.
For everything, okay, okay. And actually, one second question. So you mentioned also infinity products for the counter terms, the set terms. If you would do that for more general gauge theory, would you expect to find, let's say, restrictions on renormalizability from the infinity relations?
Okay, so so first of all, so even for by the way, I didn't mention, but pi cube theory is renormalizable for d equals 6, right? So basically so we know a lot of things about the renormalizability in the ordinary formalism or canonical quantization or path integral. My message that can be translated into quantum theory. So there is nothing new and nothing, but at least everything can be translated in this language. Then, if this theory is not renormalizable, then we need a lot. We need infinitely many counterchange. So that's the usual thing as we learn in the quantum theory course. I'm sorry, is this your question? So in the case of gauge theory, so if it is renormalizable, we have only finite counter terms to the action, which is described also in terms of the board phase n. So I'm just saying that everything can be translated, even for the gauge theory, which I haven't worked on, but I think I should work with some interested students, right?
So if I can also ask something. So the higher M's, they contain some integration over something like analog of modulus, or like something like Schwinger parameters.
For pi cube theory?
Of this theory, yeah.
Of this theory,
Yeah, phi cube.
it has nothing to do with modular space.
No, I mean Schwinger. I mean there are Schwinger integrals in quantum field theory. So are there some
maybe,
integrations involved in the definition of the higher amps? That's one question. And the second question related that the amps do depend on the regularization parameter, like let's say if you do DIMREG or something like that.
Okay, so you asked two questions. The one question is you asked me about the higher M. So you mean M3 or M4 or something like that? Right?
Yes.
Actually, that doesn't exist for phi cube theory just because of renormalizability, right? So we need a counter term for the actually this backup slide was useful. So in the quantum theory, M consists of only M0, M1, M3. No, M2. No M3 or no M4. But then for each term, we need an infinitely many counter term order by order in G. But it is but this is true only for the actually I should have mentioned somewhere. I secretly chose D to the dimension D to the 6 for renormalizability following the Sredeniki's textbook.
Sorry, if I understand correctly, so your quantum A infinity algebra in the phi cube case is essentially good old A2 algebra.
Good old, sorry? Good?
A2 algebra.
Yeah, A2 algebra, yeah.
Okay, and there is
even
nothing,
in quantum case, yeah.
There is nothing quantum about the algebra itself.
It's quantum because I didn't wrote a quantum infinity relation, but then infinity relations are modified to include terms involving U. Just like for you, maybe if you remember the action of cross-link field theory, classical action satisfied L infinity relations, but then you need a H bar correction to the action. They satisfy quantum as maybe there are many names, right? The L infinity relations with quantum corrections or something like that. So there are additional terms, and then the quantum master action should satisfy, right? It's the same thing. So the relation is extended to include more terms in the quantum case.
This formula on your slides?
Actually, no.
It's just m plus u equals 0.
M plus U equal to
But
0.